Hello, and welcome to Unnatural Numbers, a brand new YouTube series where we finally get to talk about the number one in excruciating detail, followed by the number two, the number three, and with any luck, we'll get through all of the numbers before the end of the universe. Today, I'm joined by Christian, who is a man who does a million things, but is primarily a software learning developer at Newcastle University, and Paddy Moore, a very enthusiastic nerd and also a maths teacher. I'm Ben Cornish, a professional mathematician by day and unprofessional mathematician by night, and we are going to be talking about the number one. So first up for the number one, it's going to be my fact today. And my fact is that the number one is the most common number you can think of. So let's see if we can come up with a bit of an experiment between us to begin with. I'm going to ask you to pick a random number, and I think that the number one is going to come up more often than, say, the number seven. Are you ready? I'd like you to both think of a number between 1 and 3. Off you go. Ooh, okay. What was it?
It was 2.
It was 2. Oh, okay, right. Christian, what have
Sorry,
you got?
3 for me.
Okay, so 1 still didn't come. I was thinking of 1. So that's 1 out of 3 times the number 1 came out, but definitely more common than the number 7. Now, that might not sound too crazy, but let's think about how we distributed those numbers. Because really, I'm not actually here to talk about the number 1. I'm here to talk about statistical distributions. What we were just doing is an example of a uniform distribution, where we picked a starting number and an ending number, and then every number in between was just as likely to be picked. And hey, as if we planned it, we all picked those 3 numbers, 1, 2, and 3. But have you ever wondered what would happen if you had any random number as your upper bound and then looked at all of the numbers that could be picked? Now, you might be thinking that still all of the numbers are equally likely, but I'm going to draw your attention just to that very first number. And this is what we would call Benford's law. So Benford's law says that the first digit of most numbers is the number 1. Now, that sounds paradoxical in nature, because surely if you take all of the numbers that exist, they're all equally frequent. But if we focus on the numbers that we actually find, the ones that we find in the real world, the number 1 comes up more often. And that's because in the real world, most numbers are distributed in only really a small handful of ways, one of them being the uniform distribution. So to evidence this, I think I can show you some of my programming. I've gone on to Python and I've devised a little bit of code here that is going to start picking some random numbers. And I've done this in a few different ways, and I'll briefly talk you through it. I'm going to pick a starting random number to be the upper bound, and this random number might be anywhere between 1 and say 100, and then in that range, pick 1,000 random numbers. From those 1,000 random numbers, I'm going to then sort them into their first digits and see which one comes up most frequently. So this is my very first experiment. I'm going to call this uniform 1. And let's start off by picking a random number, let's say between 1 and 200. Does that seem fair? So if we pick random numbers between 1 and 200, hey, look at that. 58% of them start with a 1. Can you see any problems with that?
That's yes, because there's more than half of the numbers have a 1 in them. That seems a bit rigged.
Well, I mean, you're right. I was slightly cheating there, wasn't I? So I've picked an upper bound where half the numbers are number 1. Okay, so maybe if I change that to say, I don't know, 2,000, that might seem a little better as well. Although the same problem, really. I've also rigged the game to make it so that over half the numbers start with a number 1. So instead of just picking one number where I get to choose the upper bound to then demonstrate that over half of them start with a 1, how about we do this uniform distribution lots and lots and lots of times? So I've come up with a new piece of code, and I've called this one lots. And what this one is going to do is it's going to run that uniform distribution from before, but it's going to run it about 100 times. And every time, the upper limit is chosen randomly. So I don't decide the upper limit. It picks its own upper limit, randomly chosen upper limit, that upper limit itself being a uniform distribution. And then it's going to pick 1,000 random numbers in that range. And what you'll notice is, hey, look at that. Still, about 22% of them start with the number 1. And then the frequencies seem to go down in an approximate order: 1, 2, 3, 4, 5, 6, 7, 8, 9. Isn't that fascinating? Well, that's a uniform distribution. So maybe I'm cheating by making this uniformly distributed. So let's go to one of my other favorite distributions, another one that we see so frequently in the normal world. We call it the normal distribution. This is that classic bell curve shape that I'm sure you've all seen in your science classes. So here I've got the normal distribution, and I'm going to sample it with one set of variables. For this one, I've chosen a mean value of 10 and a standard deviation of 5. And I'm going to pick 1,000 numbers within this range and work out what that first digit is. Could you accuse me of cheating again this time? What do you reckon?
Can't quite see how you're cheating, but then I haven't really. Go on, how have you cheated?
Well, the way that the normal distribution works is that the mean value 10, that is basically our halfway point. And then all of the data is clustered around 10. In fact, we have this lovely rule in statistics, the 68, 95, 98 rule, that says 68% of the data is within one standard deviation of the mean, and then 95 is within two standard deviations, and 99% of the data is within three standard deviations. But I've picked those numbers 10 and 5, so that 10 is the middle, and therefore, if I go for 95% of the data, that's within the range 0 to 20. So I've cheated again by making at least half of the numbers in that range. So what's going to happen then if I don't pick my numbers for the normal distribution, but instead do the normal code? So once again, I've gone for about 100 different normal distributions where the mean and the standard deviation have been randomly selected and then sampled 1,000 data points from each of those distributions. So this is out of my hands. This is just like saying, what if I picked 100 different normal distributions, like what you might see in the ordinary world around? And hey, look at that. We still have this repeating pattern of 1, 2, 3, 4, 5, 6, 7, 8, 9 in descending order of frequency, where the number 1 comes out the most, and it works out to be about 30%. These are normal distributions, just like you find all over the place, where with random parameters, so nothing that I've engineered to happen, it just exists. Okay, well, I'll speed through the rest of them because another couple of my favorite types of distributions are not just uniform and normal, but where we have something like an exponential equivalent of a normal distribution. Does it work if I raise everything as 2 to the power of something? Yes, it does. Is that true just for one data point where I'm cheating, or is that always true? Can all exponentially distributed normal distributions work? Yes, it does. It still comes up. What happens if I have an exponential uniform distribution? Yeah, there it is. It happens every single time. And if you want, you can check through this code later to make sure I haven't just engineered these particular numbers to come up on every event. This is just a random quirk of statistics that the number 1 happens most frequently when you take samples of random data, or for that, you could read things that happen in the real world. Now, as we know, things that happen in Python aren't always the things that happen actually in the real world. So to put your minds at rest, I've got 2 particular examples that I want to share with you of things that do happen in the real world. So this first one is a list of populations of all of the countries of the world, and then looking at the first number of that population size. That's in the red. And in the black, this is what we might have expected from Benford's law, that 30% for the number 1 and moving down. I've got another example. These are various physical constants. So if you are a physicist or a scientist out there, you might know things like the speed of light or Avogadro's number or the distance to the sun. If you look at all of these different physical constants and things that come up in science, you could also check out what number they start with and plot them. And it roughly follows this law, Benford's law, to show you the expected frequency of all of the numbers. And why does this happen? I've got no idea. I just think it's beautiful that it does. And I think it's beautiful that we can show it using statistics and random sampling. And that
Do
is
you think,
my,
sorry, do you think that this implies or infers that we're missing a load of physical constants that begin with the number 7?
Absolutely, it does. Yeah, I think scientists are quite lazy and they haven't really been putting enough time into or funding into finding constants beginning with a 7. Absolutely. But yeah, that's my little talk on Benford's law.
you've sort of given the impression that it always happens, and it definitely doesn't.
What have you got?
So if you look at the ages of prime ministers, for example, none of
Oh,
Yeah.
them would start with a one.
Yeah, no, you're absolutely right.
So the
Have you got a theory as
Benford's
to
law
why that is?
applies when you've got a mix of orders of magnitude. That's what you really need. If you've got, if all your numbers are sort of the same order of magnitude, the same number of digits, then you could very easily not have the leading ones included at all.
That
You,
is a great theory, and I think we could actually demonstrate that looking at, for instance, the normal distribution, but where we only have it one time. If I go back to this, where I'd cheated and had different orders of magnitudes, you might
yeah,
notice this one is a mixture of one-digit and two-digit numbers. We could change this
yeah.
to make a mean of, say, 50, and Benford's law should hopefully disappear. Is that what you're suggesting?
I'm hoping that's what's going to happen.
Oh, hey, look at that.
Yeah,
Yeah, and now it
there we
seems to
go.
be a bit of a mix of all sorts.
Yeah.
Yeah, very good. Good observation.
So, and my understanding of why Benford's law works is that the change you need to make to get to a leading digit one is much less than the like starting from any number that to get to a leading digit one is probably much relatively much less than to any other digit. I don't know.
Yeah,
I
that
don't
makes a
know.
lot of
It's maybe
sense.
too late, doesn't it?
so so the
I'm waiting on my
change to
hand a
go.
lot.
So you're saying the change to go from like 800 to something beginning with one is relatively small compared with the change required to go to something beginning with a two.
Yeah,
Yeah, that makes sense.
something like that. Draw a
Uh,
log curve and sort of say,
Yeah, you'll notice that the law also works with any base system as well, because that
yeah,
principle of getting up to that next place value is just as hard with any base system. Another
yeah.
example where Benford's law doesn't quite work is in binary, though, because in a binary system, it's not just that it's the most likely; it's the only one.
Equally.
The
Um,
only leading digit. Yeah.
another thing about Benford's law is it's boringly useful. They actually do use it, don't they, in accounting fraud investigations to look for made-up numbers, and instantly because it has a use, it's less interesting.
Yeah, I think I agree. Is why I wanted to focus on trying to recreate it today rather than trying to explain it, because I'm going to hope of actually explaining where it comes from.
Yeah.
Um, but no, that's very interesting. Thanks. Christian, you want to talk about Legendre's constant?
Yeah. Okay. So this is it's one of my favorite numbers. Um, we're gonna go back in history a bit. Let's imagine that we're back at the turn of the 19th century, around about 1800, and mathematicians, we're starting to look at number theory. We're starting to think about it in a much more formal way than people have in the past. The move from geometry being the main task of mathematics to thinking about things symbolically and more formally is happening. And so people all around were thinking about what can we do with number theory? What facts can we prove? And Adrien Marie Legendre was looking at the prime counting function. That is the answer to the question, how many primes are there less than the number I'm thinking of? So prime counting function of x is how many numbers less than x are prime. Uh, it goes up. We can say that very easily. The more numbers you look at, the more of them are prime. It never goes down. Easy facts about the prime counting function. But uh, you might think, well, can I give an explicit formula for this function? That would be really good because using that, you'd be able to tell where all the prime numbers are. We don't have that yet. So that's too hard a fact to prove. In between, Legendre was looking at, well, can I come up with an approximation to it? Can I say for a given x, the prime counting function's value will be pretty close to something that I can write a nice formula for. And he wrote I don't know if this was in a paper or in a letter to someone, it's a sort of fuzzy back then, isn't it? That it seems like the expression x over log of x minus 1.08 something, 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 something seems to match the prime counting function really well. And this wasn't just a hunch he had. It didn't come from out of nowhere. He'd actually counted the primes, which is a fun thing to do, I suppose. Uh,
Sorry,
quite
can you
a
say
hard
that? Can
thing.
you say the formula again so I can write it down?
Oh, yes. As I was thinking this, I thought, oh, there's a graphic I need that I didn't ask for. Um, so it's x over log of x minus 1.08633, something like that.
Is that in the denominator or overall?
366 was the number he came up with, but it doesn't matter for a reason I'm about to tell you. Yeah, so that's all in the denominator.
Okay.
So x over log of x is, I think it's Stirling's approximation to the prime counting function. I don't know if that's earlier or later, but Legendre got a bit closer. I thought if you add this constant on or you take it off, then you get really close to the prime counting function. Um, and so now's the time to reveal my graph, I think, if you could, Ben.
Oh, there it is.
This is the graph of so we're sort of inversing that formula that we had down there a bit. It's what would that constant be for a given value of the prime counting function. So the straight horizontal line there is the value that Legendre had, 1.08 something. And it really does look like this curve, this graph is sort of converging on that value.
Is that a known value?
Well, it's the value that Legendre thought about. So it's that 1.08 something, something, something. Um, and that graph goes up to 100,000. So all the prime numbers less than 100,000, if that's your, so if x is 100,000, you count however many primes there are, put on the other side of your equation, then it looks like this number should be 1.08 something.
Hmm.
However, just sort of saying, oh, it looks like it, was good enough in the 18th century. In the 19th century, they changed their minds and said, no, we need to prove this, guys. It turned out that that doesn't hold forever. In the limit, as x goes off to infinity, as x gets bigger and bigger and bigger, this curve starts to come down again. And it comes down, and in the limit, that number is exactly 1.
Dun dun dun.
That's cool.
Wow.
So there was a nice period in history where Legendre's constant meant this weird number, and people were trying to prove why it was that thing. But actually, Legendre's constant is just a fancy name for the number 1.
So,
Oh, I
so
love
it's
that.
x over log x take away 1.
Yeah.
Mhm.
When you say at the limit, how do we know?
Well, it's been proved. It was quite a
That's all right
difficult
then.
proof in the 19th century. Someone came up with, but I think around about 1980. I'm remembering Wikipedia. Anyone listening can look at Wikipedia and get the actual fact. Around about
Fair enough.
1980, someone came up with a much more straightforward proof of why it should be.
And
Um,
let's check that we understand. So that's counting how many primes there are less than x.
yeah.
All righty then. Yeah, cool. I like that. That's great.
That's awesome. And also, can I chime in with some really pointless prime number facts about
Yep.
one?
Yeah.
Yeah, okay. So obviously one is not a prime number, but um like going back to Euclid, if we go really far back, they didn't even think one was a number. The ancient Greeks wouldn't even count it as a number.
Hmm.
Well, how big
And
is the number one, right? Everything else
well,
is
it's
just
just
a,
one. It's
a
just
multiple of
obviously
one.
just one. It's like philosophy in because mathematics and philosophy so tightly together. One is, and two is the first number because one is just one. And it wasn't until much later that people started thinking of it as prime because I was actually taught at school, being older than both of you, that one was a prime number.
Yeah,
My
it changed over the course of the 20th century. The convention changed, didn't it?
Yeah, I think the last printed use of one as a prime is 1956,
Hmm.
which I'm not that old, but my teacher was.
and
I mean,
your teacher wasn't going to change.
you could of
Yeah,
course use the
and
notation one prime, which is very similar to one. It's just it is a prime.
yeah, but which leads us to the reason why one can't be a prime is because it stuffs up everything else, isn't it? Because if one is a prime, then the fundamental theory of arithmetic doesn't stand anymore.
Well, it
Um,
stands, but you just need to you need to add an extra clause to the sentence, to the
I
theorem
mean,
except one.
I
Yeah.
think we could figure this out though right now, couldn't we? Because if one is a prime, then that means there are one take away log of one take away one primes less than one. So I think there are negative one primes smaller than one.
Correct.
There you
Yeah, and
go.
that would hold if one is not prime, I suppose.
I
Well,
think given the level of maths that we're trying to aim for, we should probably somebody should explain the fundamental theorem of arithmetic.
see, I always get stuck on the fundamental theorem of arithmetic part about the significance of the number one. Like the prime part just feels obvious to me, but the existence of there being a one times by all the primes always feels relevant. And I always used to think about the concept of negative primes, which seems intuitive, fine. But then what does like a complex prime look like if you change that unit of one into a different unit? Um, is there, does the fundamental theorem of arithmetic also follow in other unit bases? Um, but I don't think that's the main point of the fundamental theorem of arithmetic, is it?
That's a
No,
really interesting digression, but it's absolutely going to confuse matters if we go down it.
Christian, do you want
yeah.
to? And hey, look, we're back after a seamless edit and surprisingly full glasses of water. Christian, I think you're about to tell us about the fundamental theorem of arithmetic.
Oh, I got the short straw, did I?
Yeah,
Okay.
yeah, yeah.
Um, the fundamental theorem of arithmetic says that every, let's go natural number, has a unique prime factorization. So you can write given any natural number, any positive integer, you can write it down as the product of prime numbers only in a unique way. When you multiply things, it doesn't matter what order you do them in. So, I mean, yes, you can say 3 times 2 or 2 times 3, but those are the same thing. But apart from that, which primes you use and how many times you use them is uniquely determined for each number.
Greater than one.
Hey,
You
look, it
have to
works.
you
Well, it
have
means
to
one is the
include
empty
greater than
product.
one,
So
otherwise it doesn't work. Or rather, it becomes confusing.
yeah, I mean, if you're happy with the empty product, then it works for one, but otherwise, no.
Yeah. Yeah, I really enjoy doing this is one of my favorite things to teach at like year seven and year eight is the prime factor decomposition. It's a joy because you can do so many fun, pointless things with it afterwards. I'd say I really like it.
I like the characterization of fun, pointless things, brackets, the rest of maths. It's quite an apt description.
Well,
Yeah,
I
like
can't
maths.
deny being interested in prime numbers because I own the domain isthisprime.com.
No, you're kidding.
Okay,
Well,
we need to go and check some numbers right now.
I mean, we weren't going to do the plugs for our own private projects until later on at the end of the episode, but
I've got
that's
too
a
many
I'm
good
gonna
projects on the go for that not to happen.
one. No, genuinely, that's quite exciting. I used to use that more often than I am proud to admit when I was at
Oh,
university. So on to our next big fact. Paddy, that's you. What have you got for us today?
oh, okay. This starts with a really bad joke, and as you know, jokes are always better if you have to explain them.
Hmm.
So, an infinite number of mathematicians walk into a bar. First one says, "I'll have half a shandy." Second one says, "I'll have a quarter of a shandy." Third one says, "I'll have an eighth of a shandy." Barman gets bored, slams down 1 pint onto the counter and says, "Problem with you mathematicians, you don't know your limits." As I said, definitely better when they need explaining, because this is when the idea of limits comes in. And the limit is an idea that really gets developed in the late 19th century, mid 19th century by Cauchy and people like this. The idea that if we keep going forever, something will tend towards, I'm being very vague and hand wavy because that's my understanding is very vague and hand wavy. as we tend towards something, it gets closer and closer to a specific value. And in the limit, if we go on forever, if we continued that for an infinite amount of time, it would equal one. And so if we take the numbers a half plus a quarter plus an eighth plus a 16th and so on forever, we'll get to one. And this, going back to the Greeks, this is one of Zeno's paradoxes because he tried to argue that movement is impossible using the idea. Yeah, no, this is genuinely true. It's the first Zeno of Euler. There's about seven of them, all maths philosophers of varying degrees of brilliance.
Although
I
the
don't think
second
the
one was
eighth
only
Zeno
half
who
as
said 11.
brilliant as the first, and then
That's
the next one's
correct.
only
And
half as
then,
brilliant.
but we don't have an infinite series of Zenos, so we don't get to a whole complete one. So Zeno's argument was that in order to reach any particular point, you have to go half of the way there first. And then to reach the next, to get from where you are to the next bit, you have to go half that way again. So half of a half is a quarter. And then to get closer, you have to go half of that distance, half of the quarter is an eighth, and so on forever, proving that, you're never going to get there because there's always going to be that little distance away, which that little distance, again, from the number one, is the source of so much problems for mathematicians going through time, from Zeno about 400 BC all the way through to Newton, who didn't fully resolve it and came up with a quite hand wavy, similar to my understanding, way of dealing with these infinitesimals. And it's not until we get to Cauchy and people like him that we have a real resolution for why this series equals one. At the same time, Diogenes proved his answer to Zeno's argument that movement is impossible is he got up and just walked off to defeat his argument, which I think is a pretty solid counterexample.
Nice.
So, yeah, that's my love. That's my lovely thing that I'm excited about. Completely pointless and really interesting to me.
One thing it reminds me of when we're talking about an infinite series of things that then approach one and we eventually get there is that lovely one of 9.9 recurring or zero point 0.9 recurring. The one that I'm sure we've all seen on the social medias of someone trying to convince you that it's not quite true. That why is it then that if I have a ninth and then a ninth of that and a ninth of that and a ninth of that, why is it that that is equal to one as well as having a half and a half of a half and a half of a half of a half? How is it both of those infinite sums end up being one?
Oh, that's a really interesting question, and one that we can leave for the watcher.
Yeah, yeah, I think that's a good
No, no,
idea.
I want to get into this one because the reason is
Oh,
really good.
yeah,
Go
go on.
on.
So if you write your a half and a quarter and an eighth in binary,
Ooh.
you will
Sorry,
notice.
do you want me to now? Yeah, go on then.
Oh,
Let's get into
okay.
that.
So
So that is
in binary, you've got
zero point 0.1
powers of
and
two.
then 0.01. Yeah.
Yeah, yeah, yeah. Right. So you're adding all those together. So in binary, that sum is 0.11111 recurring. Now, one is one less than two. Nine is one less than 10, which is the base system you use for decimal. That's why it works.
So, is there a way we can do that for every number? So, if we worked in base three, we would be able to do that for
Yeah.
thirds repeatedly.
Yeah. So 2/3 plus 2/9 plus 2/27 plus 2/81 works the
And
same.
the same thing for 4/5, 16/25, and so on. Oh, this is brilliant. Okay.
And you might want to prove it. There's tons of ways to prove it, but you might want to do it graphically. So you can draw maybe a box and take a half of it, and you're left with something. You take a half of that. You just keep on taking a half of what's left, and there's absolutely no way you can argue that that's not getting to one.
That's a great, I've seen that picture elsewhere, and it's really impressively visual way of explaining it, isn't it?
Yeah, there we go.
There it is. I'm a little bit slow on the pen today. I really like that argument about it being all about the place value system. That's quite nice, and I think we could generalize that to n take one over n and take one over n squared, etc. For any value of n being the place value system that you're in.
Yeah.
Excellent stuff. What other fun things about the number one do you guys have to bring to the table that maybe doesn't warrant its own big speech, but is just quite a little oddity or quirk? Why do you like the number one?
Well, the other thing I wanted to talk about was just all the different kinds of one.
Mm.
So you might say, well, there's only one, and sort of by definition, we all these ones are the same sort of thing. And like one apple and one orange, like what's the oneness? It's the fact there's one of them. But that's not what I'm talking about. I'm talking about objects which behave differently to one, but for some reason we write down as one because that's just more convenient. So an
So
obvious,
things like this one here, the identity
yeah. So the
quality.
identity matrix. If you haven't encountered matrices, it's sort of a shorthand way of doing lots of equations at the same time. Linear algebra, you're multiplying things together. An identity matrix is something that you multiply anything by this, you get the same thing. It's identity. It works in the same way as one in that sense. If you multiply any number by the number one, you still have the same thing.
Well, of course, the number one is a matrix itself. It's just a matrix with one row and one column and one element.
I mean, we don't have long enough for me to talk about how far you can push matrices. Is the empty matrix a matrix? Yes, but we can have an argument about it. Should you use the number zero to write it down? Ooh. So yeah, identity matrices in group theory, where you're talking about even more abstract kinds of symmetries, but you still have operations on things. You always have a unit element which doesn't change, an identity element which doesn't change anything else. And it can be quite conventional to write that down with the number one, only in a context where it's absolutely clear that you don't really mean the number one. You mean the identity element.
Well,
So
that's why
yeah,
we tend
that's
to
something
write
I
it
think we've
with
talked about, but it's a bit woolly.
why we tend to write it with a Roman numeral, so it looks like an I for identity, but really it's just a secret one in Roman numerals.
Excellent secret work there.
Yeah, I'm going to try and reveal my t-shirt here. This is the
Yep.
node identity matrix.
Hey, very good. Right.
My pointless, absolutely rubbish fact is that one is the only number that is represented the same way in binary, Roman numerals, and denary.
I don't know deanery. Which one's deanery?
Base 10. It's just a fun way.
Go on then. As a quick vote, how do you guys write your ones? Are you left, middle, or right?
Middle.
It depends if I'm
Middle,
at
unless I'm
school or
being
not.
fancy. Sorry.
So I teach internationally, and I get all sorts of different ways to write the number one from my students. The one that annoys me the most, I think, is the German one that is like the middle one, but very, very strong.
Yeah, I would say either the one on the left or the one on the right are acceptable. The one in the middle is wrong.
Well,
Ooh,
go take that up with Central Europe, see how
Yeah.
they react.
the one in the
I
middle. It's the
I
one
don't
I
have a
love.
one in the middle. No, I tend to write a one like that when I'm writing lots of numbers, and when I'm writing a one on its own, I tend to do a capital one.
Yeah.
Obviously, this is the capital version of the number. We all know what capital numbers are. We don't need to talk
Agreed.
about it. But yeah, it's a good fact about the history of how numbers came up. I had one other one to bring to the table, and that is one as the radius of convergence, which is a really fun word to say to A-level students just before they go into their exam. So the radius of convergence comes up from when we have infinite series, infinite power series in particular. So if, for instance, I might write x, and I might write x squared, and I might write x cubed, and I might just keep on doing this forever and ever and ever and ever. And you'll notice that this number is absolutely massive, isn't it?
Unless.
Yeah. So for most numbers that you put into this infinite power series, where we go up to x to the power of, and I'm going to write it, x to the power of infinity. If you put any number into this that is one or higher, it's just going to explode out of control. It's going to get far too big and tend towards infinity. But if we are within the radius of convergence, if our value has a magnitude less than 1, then maybe it doesn't go off to infinity. Maybe it's something that we can control and calculate. Maybe we can find that as a value. Spoiler alert, we can. But I quite like that. And I especially like it talking about it as a radius of convergence, because for me, it brings
Absolutely.
together this idea of one not being a single number, but instead being a group of numbers, because we can then talk about complex values and look at the imaginary part and the real part, and then say anything that's inside this circle that has magnitude 1 will converge when we take those infinite series. So I quite like that one.
I love that. I've not heard radius of convergence before. I mean, obviously, I teach this at A level, and I am totally going to use that to confuse and annoy all of the students from now on. Well, it's the only one of the digits that's in Euler's equation. So Euler's, that beautiful thing, e to the I pi minus 1 equals 0. It's the only whole number that we're going to talk about in that, which it is enough to qualify it as the best number if we assume it is a number.
Yeah, I'd argue great reason why it's not a real number. But no, that's lovely. Yeah, a really beautiful equation. Just for people who haven't seen that, let me write it down for you because it is delightful. So that is e to the I pi, and then do we say e to the I pi subtract 1 equals 0? Is that how you like it?
I really hope that's right.
I would go plus, but otherwise.
Yeah, thank you very much.
Damn it.
That's why we revise before we teach.
That's
So we're going to vote and say, do we think that the number 1 is the most interesting number that we've discussed so far?
yes.
Yep, good, cool, carried without any contention. Lovely stuff. Okay, so let's finish today off talking about a sequence. So I've gone to the online encyclopedia of integer sequences, as I always do for my bedtime reading, and I've picked out sequence 001221, which is not the sequence, that's just the name of it. And here's the first 5 digits, 0, 1, 1, 1, 1, and I'd like you to guess what comes next.
I've seen the OIS before. I'm absolutely refusing to guess what comes next. Absolutely anything could happen next. It could be a million, it could be -1, it could be 1 again.
I think it's something with like 15 digits.
Is that why
I,
it's quite a long, big box here
yeah, I
afterwards?
think that's right. And then the next one is ridiculous.
No,
The next
I've tricked you, I'm afraid. And in fact, I need to get off my graphics tablet and pick up my mouse. Delete. There it is. It is a 2. Oh, and then it goes back to 1s. So we're 1s again for a little while. It's safe. And then another 2, and then a 1, and then some more 2s, and then 2s and 1s. And then what do you reckon's going to come after this little mix of 2s and 1s?
No.
This is the point at which it just becomes
Just lots more 2s and 1s. And then we do get a 3, a 3. Look at that. Ah, 3. So
This looks a bit like there's a sequence. I think this says there's no ones, then there's 1 1, then there's 1 twice, then there's 1 1 and 1 2. Is it that sequence that we're looking at?
This is where I would
it's
dramatically
not.
reveal the t-shirt I've had made of that sequence, but I'm not wearing it today.
Is that the sequence that we're looking at?
No, it's not that.
It's not.
Oh,
If I'm counting correctly, I think this one might be number 29, 30. 30. What's special about the number 30, folks?
Is it a primorial?
Can you tell me what you mean by that word?
It's the product of the first few prime numbers, so that's 2 times 3 times 5.
That is 2 times 3 times 5. And how does that relate to the number 3 in the way that nothing before it relates to the number 3?
it needs 3 prime numbers to make it.
You are
Prime
close, but the number 8 has 3 prime numbers.
3
3
different prime numbers.
discrete
Three
primes.
distinct prime numbers to make that number. Yeah, so this is our sequence. I think it's called omega n, the counting number of distinct primes in the prime factorization.
Oh,
This is
okay.
the point at
That's
which I
cool.
say this sequence looked familiar to me, and I was fairly sure I'd looked at that entry before. I never
But
would have got that.
you didn't want to out yourself as a nerd this early on.
I wouldn't have been able to say what it was without you explaining it. But yes,
Yeah.
I've definitely looked
So
at that in the past.
So I'll be honest, I was searching through the encyclopedia, just typing in 4 1s in a row to see which interesting sequences came out with it. And it turns out, yeah, a lot of sequences just start with a whole bunch of 1s, don't they? Christian, as a test question for you then, do you happen to know the average order of AN? The average value of how many distinct primes there are before a number n?
2.
or could you work at two? It's not two, but you're not far off. So this is if we take the all of the numbers up to the nth one, add them
Yeah.
together, and then divide by how many there are. We get log of k. And don't you just love it when you see two logs in a row like that? Doesn't that just make you feel like you've got a whole warm evening of maths ahead of you? Which
The
is
thing
not
is,
dissimilar to your fact from earlier.
yeah. So the thing is, like, I can remember being maybe in sixth form, looking at things like this, like being a bit interested in maths, looking at something a bit beyond what I was learning, and seeing that kind of thing, and thinking that is absolute voodoo to me. Where has that come from? And now you've shown me that, and I've just sort of gone, yeah, it looks about right. And I don't know what's happened in between because I wouldn't be able to give you a full explanation, but that looks like the kind of thing that it would be.
Yeah, I think you've had it normalized to you now, haven't you?
Yeah, I've been desensitized to
Been
hard
in the
maths.
dark too long. Go on, a quiz question about this particular sequence. Can you tell me how long does it take to get a number that is greater than three? When does the first four come up? Who's going to get there first?
2 times 3 times 5 times 7.
Are we going to take that as
210.
a number? That's a product.
210.
210. I'll take your word for it. I don't have my calculator to hand. Nice. Any other interesting facts from you guys about this surprise sequence that you didn't see beforehand?
This sequence goes up and down,
It
which is a really
does,
basic fact about it. But I
but
said
we,
earlier that the prime counting function only goes up.
yeah.
The other thing I can say about this is it's never negative and it's never zero again.
But this one, because there are infinitely many primes, it will infinitely return back down to one. And we have no idea when it will infinitely return back down to one, of course.
Yeah.
But we do know that there's an infinite number of ones that are only two spaces away from each other because of the twin primes. Has that been
Mhm.
proven, or is that still just strongly
Oh, that's
assumed?
that's still outstanding.
So
Crikey.
that's okay. Well, maybe we could finish that tonight. What I think is a bit of a mystery with numbers is why we talk so much about the reoccurrence of primes and therefore the ones on this particular grid, this list, and why there isn't as much public attention for the composite numbers, so that just the twos on the list or just the threes. Why do we not have as much enthusiasm about things that can only be expressed as twos? I suppose there is in cryptography, isn't
I'm going to go all late 1990s Marcus de Sautoy here. The primes are the building blocks of the natural numbers. So you understand the composite numbers by understanding the primes.
there?
It's not that the primes are interesting and the composites aren't. It's that if you see any number, looking at its prime factorization can usually tell you some more about it.
I'm gonna one down you on that and tell you a less interesting thing. And I reckon we got that backwards because I reckon in its earliest form we learned more about the primes from understanding the composites. And I'll throw into the mix the sieve of Eratosthenes, which is probably not how you pronounce it, where we only found what the primes were by first of all deleting all of the multiples of a particular number. So that's using the composites to get the primes rather than the other way around.
Exactly. Do you know about the mechanical sieve of Eratosthenes?
No.
It's the mechanical one.
So you can make a mechanical one. So if you have a grid, or if you have stacked grids, like a 10 by 10 grid, and you make a hole in one of them for every second place, so that's the twos, you make another one and only punch out every third hole. Stack those all on top of each other. What holes are going to go all the way through this list of all the way through these things? Sorry, no, you block off every second one. You block off every
Oh,
third. Yeah.
so like a giant stack of Swiss cheese.
Yeah. So, or just, yeah.
Mm.
So
So
if you have that and you stack all these up, then the only holes that you can see all the way through are the numbers that are not divisible by any of those numbers that you had sieves for.
yeah,
So that's literally like the analogy is it's called a sieve, but like it's literally how that works. And you can do that. And I have one on my desk at work.
When you say it's an analogy of a sieve, you're describing a sieve. Like that's
Exactly.
literally
So
a
it is
sieve.
exactly a sieve. I
Yeah,
mean,
okay.
Eratosthenes didn't actually make a sieve to test this, but
No.
you can actually do that. And someone did and actually got some new maths out of it in the 1940s, 1950s, I don't know, mid 20th century, using light sensors. So the very early days of computational number theory, things were still analog, but you basically make this sieve. It was more like a barrel kind of thing. It was something lamer. And by shining a light through these sieves and rotating them around, whatever, he found numbers that had some special property. It wasn't just primes this time, it was something more complicated than that. By numbers that shone all the way through this sieve and were detected on the other side, had the property he needed. So that, I mean, Paddy, you said earlier on that when something has an application, you lose interest. But like this was like cutting edge, pure maths research that to get the examples that he needed, had to actually build a machine to
Yeah.
compute these things before you had an electronic
That is
computer.
incredibly cool. And these applied mathematicians just come in and steal some of our good bits every so often, don't they? That is very cool that you've actually got a work that you can build a working model of that theoretical idea. I just love that. And you said it did with light sensors.
Yeah, so I mean, you want to do this really quickly. So like grains of sand falling through a hole or
Hmm.
marbles falling through holes will happen slowly, but light, I don't know if you know, moves really quickly. So the
It's a bit
idea is that by
slippery, isn't
spinning
it?
these drums around really quickly, you can try all the combinations of these things, and just whenever you get some light through, that corresponds.
Hmm. Nice. Oh, thanks for sharing that.
That's cool.
Before we go, would either of you guys like to share any projects that you're working on that you'd like to direct people towards?
I am currently teaching a group of students who are very bright how to do maths. And if anybody else would like to learn maths, they should go and see a maths teacher.
Christian, are you working on anything at the moment?
I'm always working on something. I'm always working on multiple things. I suppose you could find me on Mastodon, which I run. Um,
Get out of town. You don't run the whole Mastodon.
yes. I mean,
Oh
you were
my.
surprised I own thisprime.com, and now you're surprised.
I'm more
Yeah.
impressed by the isthisprime.com because that's the website I've actually been on. Nice.
Yeah. So yeah, I'm on there. Lots of other mathematicians on there. You can talk about maths like this. It's a fun place to be.
All right, thank you very much. For me, the project I'm working on at the moment is, of course, this very YouTube series. This is the Unnatural Numbers chat show slash panel show that we're trying to set up to get more people talking about maths out loud in perhaps a way that they've not done before. So if you are watching this and you would like to have a go at talking out loud, practicing your public speaking and just getting out there and doing something, then get in touch and you can be welcomed and invited onto the show. There's going to be a form in the bottom of the description that you can click on and fill out, and that will give me your contact details, and I'll be in touch and get you linked in. And then you could join us on the show and be part of the maths royalty that we get on here already, like Christian, King of Maths on, and of
Just
Is It
Christian,
Prime
right?
fame. And Paddy, I'm sure you are just as famous in your classroom as well. But if you want to have a go, honestly, do get in touch, and we'd love to have you on the show. Or the other thing I work on is a history of maths podcast. If you're interested in the history of maths, check out the Mathematicians podcast. Until next time, then, I think that's all we've got for today. So join us in hopefully a fortnight's time, where we'll be doing episode number 2, where we discuss the number 2. See you then. Bye bye.
Bye.
The great thing about being a maths teacher is I think I would be lovely to be a maths teacher, because to many people you will be the best mathematician they've ever met, and the one that they will remember as
I
being.
know, and that's a worry.
No, but in a positive
I
way. Like
I I
people will
really
look back. There will be
yeah.
people who look back and think, "Oh, Paddy, Mr. Moore always knew what. Oh, Mr. Moore inspired me. I remember that because Mr. Moore taught me that."
Mm.
I think that's a lovely thing.